Hello again from Digicool Things. Recently I've been going through a lot of archive storage that I've had since way back in the day. There's a bit of background. I was a teenager in the late 70s, early 80s, which was the early days of 8-bit microprocessors and computing projects. I started off with an interest in electronics, which in that day and age quickly turned into a focus on digital electronics, where I was building TTL-based circuits. And we all had our eyes on the hot topic of microprocessors, which in that day and age weren't available to all of us because they were quite expensive. And I think as a teenager I was probably working a school holiday job, earning I guess maybe 50 cents an hour or something like that. Anyway, this board here is a 6809 based WireWrap board that I would have put together in the mid-80s, I'd say, based on the date codes on the chips. As you can see, it's a WireWrap board, which is how we did things in those days, in particular digital electronics. And this card is a Eurocard, which has a 64-pin dual row Euro connector. And that was the bus I was using. So this was a CPU card. I've also got a card of a 6847 video display generator. But anyway, I pulled this out. It was pretty dusty. I've given it a bit of a dust off and also eased the chips out of their sockets and dropped them back in again just to break the oxidation that would have occurred over the last, what would it be, 35 years maybe. And I thought it'd be interesting to get this up and going. I've got absolutely no documentation on it. Back in those days, of course, we didn't have computers, so all the designs for this was based on what you drew up on graph paper with good old pencil and a rubber. No computer-aided design in those days. In fact, the only tools we had was I found. This was my original WireWrap tool, which I used initially, which I later replaced with this wonderful little device here, which was the OK Machine and Tool Corp JW1, which was a Just Wrap 1 tool. And this was awesome because you could put your 30AWG WireWrap wire on here, feed it through, and basically just do your wire wrap and go point to point and slide this down to cut when you wanted to effectively lock the wire, which broke the end of the wire and terminated that wire link. So that made life a lot easier. The other thing I discovered while hunting around was, in terms of the tools we had available, this here is a homemade logic probe, which I would have made around the same time in the early 80s. As you can see, homemade etched board. Those traces would have been drawn with an etch resist pen back in those days. I found this in storage with all these wires wrapped around it, and the insulation's broke. So these are really stiff, and as you can see, the insulation's just breaking off because it's so old. But this was basically a logic probe, homemade, combined with an analog multimeter, and that was pretty much all we had to debug and fault trace our own design computer boards. There was no internet back then. We didn't have computers. We had basically these tools, and we had our data books and what data sheets we could get hold of. Let's just move these out of the way and I'll show you the data book. So this one here is the Motorola Microprocessor Data Manual, quite a thick data book, and that one there was, let's see, 1981. So this would have been my Bible. This is where I went to for all my data to figure out how to build these things. And you can see in the table of contents you've got your 6800 8-bit processor through to 6809. The microcontrollers 6805. If I have a look at the index of the data sheet, you can see all the key Motorola devices from the time. Your 6800 through to 6809, 6821 PIA, 6840 timer, 6845 cathode ray tube controller, 6847 was the VDG, video display generator, 6850 ACIA, communication interface adapter, 6875 clock generator for the 6800, and we even have the 68000 in here, which must have been a pretty early, can't recall which year that was released. Page 661. Let's have a look. Yeah, here we go. So advanced information, and that was on a 6800 4 megahertz through to 10 megahertz. I always remember I never actually owned a 68000 processor because I remember back at the time that was a dream to be able to build a system based on that. But as a teenager back then, to buy the chip was just cost prohibitive. It would have been hundreds of dollars, I guess, which would have equated to probably a year's pay back then. Anyway, this book has held up pretty well. The bindings are probably starting to get a bit shady, but it's been in storage as well. The other book I've got, which relevant to this board, is the 6809 programming manual, and this one's the original issue, 1981. And this was a great reference book for programming the 6809. So you'd go to the data manual for the electrical and connectivity details to actually build your design, and then this was your go-to for programming. And the interesting thing about this book was in Appendix B there was the Assist09 monitor program full listing. So if I show you through here towards the end of the book, you can see there's the listing of the Assist09 monitor. And as I say, back in the day you didn't have the internet, you didn't have computers, so this was your Bible. And designing this board and building it, you can see there's a 2732 EEPROM there, and it's almost faded off, but on the sticker I've got Assist09 written on there. And back in the day I remember literally keying this monitor program in from this book with a hex keypad on a 6800 system. That was the Dream 6800. So the Dream 6800 was my first 6800 based system that I built, I think in 1979 from an Electronics Australia project. It's something I'll have a look at another time. But I used that to build my first homemade EEPROM programmer for programming EEPROMs, and had to write the code. Because back in the day, if you wanted to program an EEPROM, you not only had to buy the chip, you had to actually build a programmer for it. As a hobbyist, of course. I mean, we didn't have the money to go out and buy a professional programmer, so you had to basically build your own programmer and write the code, in this case in 6800 machine code, to program the chip based on the programming specifications in the datasheet. So I would have keyed all this in using a hex keypad. I can even see in here there's places where in the listing, not all the, for example, where there's characters listed where only the first byte is actually shown in the listing. So I've handwritten in pencil the hexadecimal codes for the ASCII characters, so that I could actually key all this in. So I think this is a 2K monitor program. So I'd key all that in, and obviously had to check all my keying for any typos, etc. You can see all this hand-coded ASCII characters down here. So it's kind of interesting to remember just how we had to do things back then, because we take for granted the tools that we have available these days. That makes life so easy. When you think of the old logic probe and how the only indication we had when we were trying to debug one of these was whether we had a high signal, a low signal, or perhaps a pulse. But you didn't have any information on frequency or even the condition of those signals. But somehow we managed to make things work. So anyway, let's just have a closer look at this. I hope to get it up and running again. As I say, I've just dusted it off, and I can see for a start that the crystal's not here. So I've obviously at some point I've stolen the crystal. There is a crystal over here, but that's for the baud rate generator. Anyway, let's have a closer look. Right, might as well use my original WireWrap tool as a pointer. So looking at this board, you can see over here we've got a 6809, that's a 68A09, which is the 1.5 megahertz part. There was a 6809, like the 6800 series, there was a 68A09, a 68B09, and the original 6809. So the A was a 1.5 megahertz, the B was a 2 megahertz part, and the original 6809 was of course 1 megahertz. This is the non-E variant, so the original 6809P for plastic package. You would connect a 4 megahertz crystal across two of the pins, which was divided internally by 4 to give you a 1 megahertz clock. So for a 68A09 you would have a 6 megahertz crystal, and a B09 you would have an 8 megahertz crystal typically. They were dynamic parts, so you couldn't sort of stop the clock. There was a minimum clock speed as well, but certainly the clock speed would be a maximum of the specified value. So we've got the processor down here. Have a closer look at that. Right, so here and here we have two optical buffers. They'll be the address bus buffers. As I say, I haven't got, I couldn't find any documentation for this board, so if I need to debug it, I'm probably going to have to reverse engineer some of it, but most of it's reasonably obvious. So these two, as I say, will be the address bus buffers. Below that we have an LS245, which is a optical transceiver, so that was typically used for the data bus buffer. And then we have a 367, which is a hex tri-state buffer, which would be buffering the control signals, the clock, read write, etc. Would be going through that. Now the reason why I've got these buffers on here is because this was a CPU board to drive a bus, and a 6809, I checked the data sheet, typically the fan out capability, the address and data bus on this could drive a maximum of 4 LS-TTL inputs. So there wasn't a huge amount of drive. So you didn't need these buffers if, for example, you were just building a small single board computer where you were just driving, maybe a RAM and a ROM chip and a couple of peripheral chips like a PIA, etc. But if you're wanting to drive more than that, then you did need to buffer the address data bus and control signals. Now these buffers are all tri-state, which, similar to the outputs of the processor, if there was a BA signal out of this processor which was bus available, so when it was put into a DMA mode via a DMA request, the processor could actually turn off the address and data bus and some control signals and make them go tri-state, so that the bus was available for another master to control the bus. So these buffers, the enable pins on those, will be tied to the BA signal out of the processor, so that when the bus available is asserted, that would also disable these buffers and therefore make their outputs tri-state to free up the bus. Right, so over here, as I say, we appear to have a missing crystal, because those will be the two, they look like two 22 picofarad capacitors, which will be for the crystal. And we also have a row of what appear to be 4K7 resistors here. So these will be all pull-up resistors for various inputs, for example, the interrupt request, and various other inputs. Then we have a electrolytic capacitor and a push button, so that'll be the reset. The electrolytic providing a power on reset. Right, and then down here on the left we have the glue logic. So first up we have a 74LS14, that's a hex inverter with SMIT trigger inputs to clean up signals. So that will be used as part of the reset signal to provide a nice clean reset transition. Probably used elsewhere as well. We have two 74LS10s, which are triple input NAND gates, and an LS32, which is an OR gate, standard OR, 2-input OR gate. What do we have here? Another hex inverter, and so those chips combined will be to do with the glue logic for all the address decoding, etc., for the ROM and RAM, etc. Down here we have a 74LS138. That was the common 1 of 8 decoder, which would be, I would guess, that will be the decoder for the I/O, because we have 3 I/O chips on here, so they use 3 lines of that. Right, and then we have, what do we have here? We have 2732A, which is a 4K EEPROM that has the Assist09 monitor. Well, I hope it still has the Assist09 monitor in it after 35 years. It's very possibly had a bit of bit rot, so I have to check that out. The Assist09 monitor itself was 2K by 8, and this is a 4K EEPROM, so that would only be taking up half that EEPROM, with the other 2K available for your own home-written extensions. The 6116 was a 2K by 8 static RAM, which would have been the go-to RAM in the mid-80s. I remember my first 6800 board was based on the 2114 static RAM, which was 1K by 4. So you had to have a pair of those for every K, so this one chip replaced 4 of those. I also remember back then, looking at the 4116 dynamic RAMs, where you could get 16K by 1 in a single little chip. That was magic at the time, but I also remember that those chips were probably about $20 each back then, which was a lot of money. And I think I remember once, actually saving up and buying one chip just so I could play around with it. And, the ability to store 16K by 1 bits was in this little tiny chip was quite amazing. Anyway, I digress. If we go across here, down the bottom of the board, this will be the baud rate generator for the 6850 ACIA chip. So we've got a 2.4576 MHz crystal, and next to that is 7404 hex inverter, which will be the oscillator circuit for that, and then next to that we have a 4040, which is a CMOS counter. Now that'll be to divide down this clock signal, and obviously 2.4576 is the frequency which will divide down evenly into various standard baud rates. And then we've got an 8-way dip switch here, which will obviously be selecting the different outputs of the 4040 to feed through to the transmit and receive clock on the ACIA chip. One of these is switched. I have no idea what these are, but I would imagine from the early 80s that the lowest setting on this is probably 300 baud, I guess, maybe even lower. If we're lucky, that might go up to 19200. 9600 or below was more common back then. Possibly that's 9600 selected, I'm not sure. We'll find out. Okay, I know I've got a 68A50 here, so that again is 1.5 megahertz rated. I note this chip here is a 68, get that in focus, 68B40. So the 6840 is the PTM or programmable timer module. I'd have to check the data sheet. I think from vague memory that had perhaps 3 timers in it, 16-bit timers. And I do recall with the Assist 09, the standard configuration for that monitor was to have a 6850 and a 6840. 6840 was optional, but by having this you enabled the ability to do single stepping and tracing, because it could use the timer on this to trigger an interrupt, to effectively interrupt each opcode as it executed. So we have a 68B40, so that's actually a 2 MHz rated part, but obviously this board will only run 1.5 MHz with the A processor and ACIA. And then what have we got? Top of the board here, we've got a 68B21, again a 2 MHz rated part. That's the PIA chip, which was probably made an appearance in every Motorola 8-bit product. So that's your basic 2 8-bit GPIO ports, with a couple of extra lines and interrupt capability, etc. So that was your standard parallel I/O of the day. This little connector down here, based on its location, I would suspect that's the serial port. We're only going to have TTL levels here because I don't have any RS-232 level translators on this board. That would have made sense because back in the day, I wouldn't have had a proper serial terminal. As I said before, obviously we didn't have computers available to us back then, PCs, etc. I mean, by the early 80s, yes, we would have been getting into things like the Commodore 64s and those sorts of things. But at the time of building this as a teenager, those were luxuries I didn't have. I didn't have a computer at all. Most people didn't have a computer back then. So in order to run a terminal, this is a whole different story, but back then we had to build our own terminal. We'd have an old TV and you would have got an old keyboard from somewhere, and you would have had to wire that up to your own keyboard encoder. And then you would have built your own TTL based video display unit, reaching back, I think from memory they were mostly sort of 64 by 16 characters on a TV screen, but that was how we had to do things back then, and it was fun, challenging fun. Anyway, that's the board. Let me just turn it over so I can show you. I mean, for a start, you can see how dusty this was. I have dusted it off, but you can actually see there's still quite a bit of dust remaining. And if I flip this over, you can see there's the wonderful wire wrap. As I say, back in those days, to make a circuit board was a pretty big chore, and when you were dealing with digital electronics, wire wrap was just the obvious way to go. You could use a we still did prototyping on breadboards, but as soon as you sort of wanted to build sort of a one-off of a project, wire wrap was just the obvious solution. And also, wire wrap was brilliant for circuit board density. I mean, it's fantastic. I mean, to get that density on a circuit board, you'd be lucky to do that with a double-sided circuit board. You'd probably need to go to 4 layers, which would, just something you didn't have back in the day as a hobbyist. I think to get this going again, the first thing I'm going to need to do is find a crystal to put on here. A few crystals in here. I've got an 8 megahertz crystal, 12 megahertz. I might just use a 4 megahertz crystal. Just go with the standard 1 megahertz clock speed of the processor, even though it's a 68A09 part. Mainly because I don't have a 6 megahertz crystal in my tray. So I'll need to solder that on. I'll need to figure out a few other things like which connections are power, etc. And I'll need to also work out I'll have to just understand what the connections are here to figure out what baud rate settings we have, and just trace the wires to find where my transmit and receive pins are on here, so I can wire that up. I got just use one of these TTL to USB adapters, and we'll see if we can get power. As I said, the first thing I did was thoroughly dust this off. Well, thoroughly, I got as much dust off it as I could, and I have actually leveraged up all the ICs just to break the oxidization and then reinsert them, so you would hope you've got a good connection. I mean, one thing too about wire wrap was it was pretty long term and hardy, quite a reliable connection. Anyway, time will tell. That's it. Thanks for watching.